Hi everybody, we're going to start the third part of this presentation for week 3. Hopefully you'll be able to follow. If not, I'll set up a discussion board to ask questions on. I'm going to ask that if you're using version 8, you flip to chapter 8, page 233. We're going to talk about blueberries here. And if you're in version 9, page 235. So the situation, if you read that particular problem, and let me give you kind of the background. It's a question about cognitive functioning. Some of you may have actually heard that if you think you're going to lose cognitive functioning, it may be good to eat antioxidants, including blueberries. So this is kind of a blueberry study setup. And let's actually look at some of the basics here with the blueberries here. And if we were to look at the blueberries here, we can see that we know, according to this example problem, that if we deal with people who are 65 years of age, that when we give them what a card sorting task, a cognitive test if you will, that usually people on this cognitive test get a score, an average score of what? 80. So in the population, we know that 65-year-olds usually have a cognitive score of 80, a standard D with sigma of 20. So we've got these blueberries, and we're interested, if we test a group of people that have the blueberries, will the blueberries actually help the cognitive functioning? And so notice, in this particular case, they say that the sample has 25 adults. So we're going to need a new situation here. We're going to need some new formulas, because now what we're going to try to do is we're going to try to evaluate when people get these blueberries, does it really help them out? So what we're going to try to figure out here is if people get these blueberries and their score is higher, is this higher amount significant or not? So we're actually going to, for the first time, look at this idea of statistical significance here. So if you knew that the average score was 80, would you rather have a group that got a score of 84 or 94? Well, hopefully the obvious answer there is 94. And so the idea is we're going to look at the data that we're actually given in this particular problem and try to go through a process to evaluate, is there a statistically significant improvement when people get blueberries? And so the question here is based on a group. Is there a difference here? So we're going to actually have kind of an old formula and a new formula. In the past, we had a formula, the z-score. Remember the z-score? Z equals x minus mu over sigma. So what did all that stuff do for us? Well, you could figure out if you're an individual how you did relative to a group. So the Ohio State example of I got a 45 on a test, how did I do relative to a group? So the old z-score formula, basically the single subject z-score formula, said if I got this score, how did I do relative to a group? Now the new z-score formula is a bit more complicated than that. For this new z-score formula, which in your book, it's kind of shown in your book. It doesn't quite read the exact same way, but it is in chapter 8. It's on page 240. It's the formula on step 3 on page 240. For version 9, it's page 240. For version 8, it's on page 237. So this new formula, let's take a look at this. Z equals, and then the numerator, x bar minus mu. You know what is different about this numerator here than the previous formula? Can you see what's a little different? Mu is the same, so you're comparing a score against mu, but in the old formula it was just one person against a group. Now it's x bar. So now it's a group mean, and in psychology, all the time we use group means, we use sample information. X bar is also a sample, so we're going to try to look at this sample and see if this sample gives us enough evidence to say we are statistically significant. So the numerator in the new formula is generally given the term treatment effect. It's called the treatment effect. Treatment effect. Do you want that number, do you think, to be large or small when you do the z-test? Hopefully you gave the answer large. The researchers who are giving people the blueberries, they know mu is usually 80, and hopefully when they get these blueberries, they're hoping that the mean is going to be quite high. And actually for this problem, I want you to use, and it says it a little bit later, the score of 92. they give a little bit later, I believe. Yeah, so let's use the score of 92. So the numerator is called the treatment effect, and we want that number to be large, because if a group of 25 people get blueberries and their mean is 92, that would mean the blueberries are probably working. So the numerator is often called the treatment effect, and we want the treatment effect, x bar minus mu, to be a large number. So I hope that makes sense for everybody here. So that is the numerator. The denominator. We got to go into some detail with the denominator here, but the denominator is a little more complicated than this. The denominator is given the general name of the standard error of the mean. The denominator. Notice the old denominator with the old formula was sigma. Sigma meaning the standard deviation. Notice the new denominator. Now it's not just sigma, it's sigma divided by the square root of n. It's sigma divided by the square root of n. And the question is, well, why do we have that? Well, the reason we have that is because now we're not dealing with just one person, we're dealing with a sample mean. So we have to take into account how many people are in our group, the sample mean. So the standard error of the mean is equal to sigma divided by the square root of n. This is called the standard error of the mean. Do you think you want this number to be large or small? Standard error of the mean. We actually want that number to be as small as possible. And so the idea here is that sigma is the standard deviation, and then divided by the square root of n, we want the sample size to be as large as possible. So that denominator is called the standard error of the mean, and we want the standard error of the mean to be small because that's going to really help us out. I have to go into a little tangent here, so I'm going to stop the acoustics on this one now and continue on.